Okay, so today we're going to be looking at integration techniques. This lesson follows from looking at the standard integrals that we've seen that are on your formula sheet. So at the start of the course we looked at using long division and partial fractions. They can help us do integration. So the first example we'll look at is when division can be used. So using division to help integrate. Okay. So example 1. I want to integrate x over x plus 4 with respect to x, okay? So this would not fall under any categories we've seen before regarding standard integrals. So we need to find a way on how to integrate this, okay? So if I do long division on the left-hand side here, let's drop that out, the one next there. I've got my function x down here, okay? So x plus 4, the only thing I can multiply that so I can cancel the x's, maybe that's what we're trying to do with long division. I can times this by 1 and then subtract it, that means the x's will cancel. So I'm going to times that by 1, put the 1 up there as a recording, and I'm going to times x plus 4 by 1, so I'm taking away 1 lot of x plus 4. Okay, like that there. Okay. Now, x take away x, okay, that leaves us with 0, that means I've cancelled the x's, that's good, I've reduced the powers. And then I've got nothing, take away 4, I end up having negative 4 as a remainder. So what the integral x over x plus 4 becomes, with respect to x, well, x plus 4 fitted into x one whole time. So I've got 1, then I've got minus 4, so it's minus 4. Because minus 4 is my remainder, it's minus 4 over x plus 4 with respect to x. Okay, so that's what I've got. Now just to tidy that up so it looks a bit more proper, we'll put the minus out to the front. So minus 4 over x plus 4 dx. Okay, and now I can integrate both those terms. Okay, so I can do that. So if I integrate 1, well, that's from higher, I get an x. If I want to integrate this, well, the 4 is going to be at the front. So I've got something over x plus 4, which is in your formula sheet. You wouldn't be able to do that last year. That's using log. Okay, so then it becomes log of x plus 4. Okay, so that's using the log stuff that we've done in the previous video. Times by 1 over the derivative, but derivative is just 1, so that's fine, nothing else changes. Plus c. Okay, so using division can help split the function that you've got into separate terms that you then can integrate. Okay, so that's where division can be used. Okay with that first example, folks, yeah? Right, second example, we'll look at using partial fractions to see how that can help us. Okay, so using partial fractions, these can be very common exam style questions. Okay, so they give you something to integrate, but they ask you to split up in partial fractions first so that you can integrate. Okay, so let's look at example 2. We want to integrate x plus 16 all over 2x squared plus x minus 6 with respect to x. Okay, so again, there's nothing that we can do using any of our standard integrals that allows us to integrate this as it stands. Okay, we can't do long division, the power on the bottom is bigger than the power on the top, so that wouldn't work either. So the only thing we can do is try and see if we can split this up using partial fractions. So we'll let x plus 16 over 2x squared plus x minus 6. And our job is to try and split this into partial fractions. First of all, I need to factorise the bottom, the denominator. Okay, so trinomial, so we should get 2x and x. If you do that properly, what goes into the brackets becomes 2x minus 3 and x plus 2. Okay, so that's what that becomes as factorised form of the denominator. So if I've got two brackets, on the bottom I can then split up in partial fractions. That's a over 2x minus 3 plus b over x plus 2. Okay, I'm going to put in brackets here. That's type 1. Okay, that's the first type of partial fractions that we saw. Okay. Right, cross multiply. So to get the same denominator, we're going to get a multiplied by x plus 2 plus b multiplied by 2x minus 3 all over 2x minus 3 x plus 2. Okay. So that's just from partial fractions earlier on in the course. Right, we then equate our numerators. So x plus 16 equals a bracket x plus 2 plus b bracket 2x minus 3. Okay, now we're going to pick some x values to work out what our values of a and b. So let's first of all let x equal negative 2. That'll cancel the a term. So on the left hand side I'm going to get 14. A will vanish. So 2 times negative 2 is going to give me negative 4. Take away 3, that's negative 7. So that's negative 7 lots of b, which tells us that b is negative 2. Okay. So to get our a value, we need to try and cancel the b bracket. So in order to do that, we're going to let x equal 3 over 2. That would cancel the bracket that's attached to the b. So on the left hand side, okay, 3 over 2 plus 16, that gives me 35 over 2. Okay. The left hand side, sorry, the right hand side, okay, put 3 over 2 into the bracket attached to the a, so 3 over 2 plus 2 gives me 7 over 2. Lots of a. Okay. Times both sides by 2, therefore that's 35 equals 7 lots of a, which then tells us a equals 5. Okay, so we've worked out our two values for both a and b. So I can now split my function up using partial fractions. So the integral of x plus 16 over 2x squared plus x minus 6 becomes the integral. Okay, a was 5, so it's going to be 5 over 2x minus 3 then because b is negative, negative 2 over x plus 2 dx. Okay, so all I've done is done partial fractions to get that first function split into that there, okay? I can now integrate both those terms there on the left hand side. So what to do always, okay, it's always good to take a constant out, especially if it's on the top. So if I brought the 5 out, that's going to be 5 lots of the integral 1 over 2x minus 3 dx minus, take the 2 out, the integral of x plus 2 dx. Okay, just so that you can maybe see what's actually happening with your rules a lot clearer on your formula page. Okay, so again we need to use our logs here, okay, because we've got 1 over a term that's got the highest power x. So that would be on the first function here, 5 times log 2x minus 3. Okay, but then I've got to differentiate the bit in the bracket, which is 2, so I've got to times it by a half, because when it's integration it's 1 over the derivative. Okay, minus 2 log x plus 2. Differentiate the bracket, I just get a 1, so nothing's changing there, plus c. Okay, tidy up what you can. Half times 5, so you get 5 over 2 log 2x minus 3 minus 2 log x plus 2 plus c. Okay. Are we okay with that second example, how partial fractions do it? So it allows you to integrate a function that originally you cannot, okay, just by splitting it up, okay? Right, I've got one last example to show you where both division and partial fractions don't really help us, but you can still see a technique that can help you for this. Okay, so let's look at example 3. Okay, so when we cannot use division or partial fractions. Okay, so let's look at integrating x plus 3 over x squared plus 4 with respect to x. So here what we can do, again, we can't use division, power on the top less than the power on the bottom. We can't factorise x squared plus 4, so we can't do partial fractions here. So therefore, we're just going to have to split this fraction up, split it up. Okay, so split the fraction. So what that means is that I'm going to divide the x by x squared plus 4 plus I'm going to divide the 3 by x squared plus 4. Okay, so I'm just splitting up everything on the numerator by divided by the denominator. Okay, and again, because we've now done that, we can now integrate each term. Okay, so here, well, this first term actually was like one of the standard integrals about the rule if you've got the function like that. So if your denominator is f of x, and if you differentiate it and you get the numerator, then it becomes log of the original function. Okay, so if I look at this first case here, and I look at if I differentiate that, I get 2x. Now I've not quite got 2x, but I'm close to getting 2x, haven't I? I'm just a 2 away. So I can just modify this by timesing the top by 2. But if I times the top by 2, I've got to do the bottom, which means I'm really halving it. Okay, so I'm just halving 2 lots of it, so I get the same thing back. So I've just not edited how the question looks, supposed to done anything there. Okay. What I'm actually going to do for that second one, just so I've got it ready, is I'm just going to take the 3 out of the front. So I've got it looking like that. Okay, so first integral, I can now use the rule that I wrote there on the right hand side. So it's going to become a half of log of the f of x function, which is the denominator, so that's x squared plus 4. Okay, so that's the first one integrated. And then over here, well, I'm going to have 3 times the integral of this. Now this is what you've just seen earlier on in a previous video. That is the tan inverse rule we can use. So here, a squared is 4. So I'm going to get 1 over a, which is just 2. A squared is 4, so a is 2. Tan inverse of x over 2 plus c. And if I just tidy up, I get that as my final answer. Okay, so that's not one that we done with any division or partial fractions, but we could just still split up originally so that we get two integrals that we can actually integrate. Are we okay with that one, folks? Perfect, thank you.